Okay, this video is a set of worked examples on log and exp. It accompanies the video which runs through the rules and some of the theory involved. Okay, so I'll just run through these. Here we go. Okay, so first of all, um, given that log, or base A, log p plus log 5 minus log 4 equals log 20, find the value of p. Okay, so, well, we're just going to apply our log rules to these, so we can actually put all these into a single argument, which is going to be p times 5 divided by 4. P times 5 over 4 equals log a of 20, so therefore we can equate the arguments, and that's just simply giving us p equals 16. Okay, so that's fairly straightforward. Um, Okay, let's go down to this one. In this question, A, B, C, and D are positive constants. Yeah, well, I think I must have stolen this from a bigger question, because we don't have B, C, and D in this bit. But anyway, log A is a positive constant. So, given that y equals this expression, explain why x must be greater than a half. Well, clearly, if it's not greater than a half, then this is the argument of this log function is going to be negative, and that we can't be having. We can't have a log of a negative number. This is the sort of counterpart, isn't it, to the fact that um, some positive number to the power of something is always going to be positive, whether or not the exponent is negative or positive or whatever. So, but yeah, we can't have a log of a negative number. So that's that. Find the exact solution of this equation. Um, so if we simply multiply both sides by the denominator here, then we've got this equation, and if we then take this multiplier into the argument of the log function, it becomes y plus 3 squared. So therefore we can equate the arguments on either side, giving us a quadratic which we solve to give us this. Now, like a lot of problems where we actually form a quadratic to solve, the solutions that come out of the quadratic don't necessarily both apply to the original problem. And in this case, of course, we've got log of y plus 3. So if we take the negative solution there, we're going to have x minus sorry, the positive solution, we're going to have something which is less than 0, which again we can't have. So we're just going to take the negative solution, like what I've actually got there. So it's actually the negative solution we've got there. So that is our solution. Okay, so right. Function f is defined by this natural log of 2x plus 1. Sketch the graph and sketch the graph of the inverse of f. Right, well, I suppose we could plot a lot of points and plot it like that, but usually the thing to do with these is to actually draw the sort of the base graph, the natural log of X as we've got here, and then do a couple of transformations onto it. So if we draw that graph, that's fairly easy to draw because that's a standard sort of graph. Here we got the natural log of X coming up through X equals 1 there. Then if we shift it by 0.5, now 0.5 obviously is not 1, but bear with me. So what that does is it shifts everything to the left by a half. It sort of doesn't like it. You'd almost expect these lines to be parallel, wouldn't you? But I think you'll find that if you take a point there and take the corresponding point horizontally across, then you'll find it basically is a shift left by zero point 0.5. And then if we then squash it um, by half as a result of this 2, then we're going to end up with this blue curve here coming down here. Okay, we've actually squashed it. This is really a point for linear transformation of graphs rather than logs per se. Um, so if you're not sure about this, then watch the video on linear transformation of graphs. Then um, yeah, so what we're actually doing is squashing this, not I half into the y-axis, but into this axis, which is x equals minus zero point 0.5. Now, if that doesn't seem right to you, then yeah, definitely go to the video on this. But what we've effectively done by that is we've done a sort of an axis shift. So that is what we're squashing in towards. And so yeah, missing a bracket there, of course. Um, Okay, so and if we wanted the actual function that this is, then what we do is we change the subject to the formula. So our method for finding inverses. So if we exponentiate base e both sides, we get that. Rearrange, we get that. So this thing is our function, um, but expressed as y. F minus 1 of y, actually. And then we just rewrite it with an x in instead of y's, and that is what we get. So that actually is the function. But we've sketched it, not by calculating it like that. We've sketched it simply by reflecting it in the line y equals x, which is the characteristic of functions and inverse functions, is that they are reflections of each other in that line. But again, that's more to do with transformation of functions than it is to do with log and x. But you often see transformation of functions and log and exp together as a sort of combined two topics combined into one question. It seems to be a favourite thing of examiners to do that. Right, so let's go down a bit further. Solve this equation. 9 to the power of 5x divided by 27 to the power of x minus 2 equals 243. Okay, so you can observe in there that all the bases are there. They are all multiples of 3, powers of 3, in fact. And so if we do a bit of conversion there, this 9 can be expressed as 3 squared. Um, to get that, if we multiply both sides by the denominator here. Um, 243 times that. Well, 243 is 3 to the power of 5. 27 is 3 to the power of 3, so we can rewrite like that. All right, and now if we divide through both sides by 3 to the power of 5, we're going to get that on the left. 3 to the power of 10x minus 5 is equal to this there on the right. So again, we can actually equate the arguments of these two functions, and we get that, work that through, giving us x equals minus 1/7. Okay, so that's straightforward. Right, 3 log x plus 2 minus log y is a single logarithm. Now, one thing is a bit of notation here, which I don't think I mentioned in the preceding video, is that LG is a sort of a notation for log base 10. A pretty awful piece of notation in my view. Much better if we could just call it log base 10. Just as with natural log len, why don't we call it log base e? Would seem much more straightforward, but unfortunately we're stuck with it. All right, so if we write this out, well, log base 10 of, well, again, we're bringing this multiplier into the argument of the function. This is the argument here. Could put it in brackets, couldn't I? That'd be log base 10 x cubed plus now a little trick here. We got no log here, but well, we have really, because log base 10 is 1. Log base a of a is 1. Um, whatever a is. So that's certainly true. So if we do that, it just helps us. So minus log base 10y. So now we've got, another step here. Obviously, we're going to apply that to the argument. So that's 10 squared. So then we can put these three um, into a single argument, x cubed times 10 squared, 100 x cubed divided by y, log base 10. Oh, okay, that's a single logarithm. Right, okay, just have a look at that if you're not sure. Yeah, right, moving on. All right, using the substitution that or otherwise solve this. Well, whenever it says otherwise, then there isn't really an otherwise. So let's just do the substitution. Now, it was very nice of them to actually give you this substitution here because it sort of makes it obvious straight away, really, that this is a quadratic in 2 to the power of x. So, if we note that 2 to the power of 2x plus 1 is actually 2 times 2 to the power of x squared, and this is 2 times 2 to the power of x, and if we write it accordingly and then do our substitution for 2 to the power of x, we get this, which simplifies to that, which of course is a quadratic, which we then solve using our quadratic methods to give us this. Right, so that just means when we unsubstitute that 2 to the power of x is equal to a half or 1. And therefore, to solve that, we're going to find then log base 2 of each side of this equation. This is a set of options here, isn't it? Half or 1. So it's going to give us x equals log base 2 of a half or log base 2 of 1, and that is equivalent to x equals minus 1 or 0. So that is that. And that's something that crops quite often is, quadratics in something, which isn't just an algebraic value, so, and very often either an exponential, 2 to the power of x, or maybe a logarithm. They both come up. Right, okay, so this one's a nice one. For variables x and y, plotting natural log of y against natural log of x. Okay, so that's going to be natural log of y vertically and natural log of x. Gives a straight line graph passing through these points. Show that y equals e to the power p x to the power of q. Right, well, a straight line through those points will give you a line that has an intercept of -7 and has a gradient of 2. Okay, you could achieve that result if you just kind of work with those numbers. When we think of the general form of a straight line, I've not written it in here, maybe I'll just put it in here to help. Y equals mx plus c. In this, our our x is natural log of x and our y is natural log of y. Okay, bit confusing that we've actually got using the same letters, but that's essentially what we've got. So that's y equals mx plus c. Right. So we can rewrite that. So that's our straight line. Yeah. So we can rewrite that. Again, we're going to bring the 2 inside the argument to give us that. And when we do the same thing with that 7, we're going to get natural log of y equals natural log of x squared minus natural log of e to the power 7. When we bring these two together, it's a quotient of x squared and e to the power of 7, which we can write as a negative exponent, e to the power minus 7. So therefore, equating the arguments, then we've got y equals e to the power of minus 7x squared. So p is equal to um, um, minus 7 and q is equal to 2. Now, incidentally, on this, it doesn't say in this example, but the fact that we've that natural log of y against natural log of x is a straight line means actually there is an underlying exponential relationship. And we may see that in another example. Variables x and y are such that when log base 10 of y is plotted against x cubed, a straight line graph passing through these points is obtained. Find y as a function of x. Now this line, from the similar argument to before, has got a gradient of half and an intercept of 4. Now here our y equals mx plus c. Well, our y is our vertical, which is log base 10 of y, and our horizontal is not x but x cubed. So when we write our straight line with the appropriate variables in there, we've got log base 10 of y equals a half gradient times the horizontal variable plus 4. Okay, plus c. And then if we exponentiate each side base 10, we're going to get 10 to the power of log base 10 of y. Okay, so the inverse a function and inverse function together is just going to give us y. Getting back to the theory on that, is equal to 10 to the power of this this thing here, which is that. Okay, so that is what we get for that one. All right. Moving on. Given that log base 2 of x plus 2 log base 4 of y equals 8, find the value of xy. Okay. So we've got that. Now we might note here that this is where this particular log rule comes in handy, is we want to convert from log base 4 into log base 2, and to do that we're basically, well, this is equal to log base 2 of y, this bit, divided by log base 2 of 4. Yeah. So we just introduced log base 2, and we could have actually, it's also equal to log base 5 of y divided by log base 5 of 4, or natural log of y divided by the natural log of 4, or anything we choose. But obviously we're not interested in those. What we want is, we want it in terms of log base 2, because that's what we've got there. All right, so, and log base 2 of 4 is, well, 4 when expressed as 2 to the power of something, the something will be 2, the exponent is 2. So that's what we've got there. So if we look at the equation here, which I should write, that's the so what we're doing is, well, we're substituting for that, we're substituting this. The 2's cancel, so I kind of missed a step out there, didn't I? And we got log base 2 of x plus log base 2 of y equals 8. First log rule, we can write those as a single argument. That's log base 2 of xy equals 8. So xy equals 2 to the power of 8. That is exponentiating both sides base 2. 2 to the power of 8 is 256. So that is what xy is. Right. Okay. Here we go with this one. Variables x and y are connected by the relationship y equals a x to the power of n, where a and n are constants. Transform this relationship. This is an exponential relationship. Actually, it's an algebraic one, but anyway, the because n is a constant. In other similar problems, you actually might be given a equals n to the power of well, sorry, y equals a times n to the power of x. That and that would be an exponential relationship. But in this case, we can do a similar sort of thing. We can take the log of both sides, and when we do that, we're going to get log of this. This is any base equals log base a plus log of x to the power of n, which again we can write as n log x. So we've got that. All right. I just twist that round, make it a little bit more obvious. So y equals mx plus c. Okay. Um, so your constant, so your gradient, and um, and well, a. So therefore, log a is a constant as well. Now, as kind of related question here, when natural log of y is plotted against natural log of x, all right, well, now we're definitely talking about natural log, not any base, but natural log of y against natural log of x, a straight line graph passing through these points is obtained. Find the value of n and a. Okay. So a straight line passing through these points has a gradient of that, similar argument to the previous question, and the intercept is given by, well, I've taken this point, y equals the gradient times x, that's the x value there, plus c, giving us c is 0.5, and the full equation of the straight line is therefore natural log of y equals 3/8, the gradient, times the independent variable natural log of x plus the constant. So that is your straight line, and therefore when we compare that to this, we can see that n is 3/8 and log base a is 0.5, but they're asking for a, aren't they? So a is going to be e to the power of 0.5. Um, and that is 1.649 to 3 decimal places. And I might just write in here, that's going to be my preferred notation, log base e, natural log. Okay, right. Okay, so that's a fly through quite a few questions, all of which are fairly typical and kind of common kind of problems that come up. So I hope you have found that useful. And thanks for listening.